Okay, so it's pronounced L'Hôpitals, but it's spelled L and then apostrophe hospitals. He came up with this rule for finding the limit of a function, and it makes it way, way easier for ones that are very hard to find otherwise. So it has to be in this form. It's got to either be 0 over 0 or plus or minus infinity over plus or minus infinity. It doesn't matter if the infinite part is positive or negative. So if we have this limit, and we do a direct substitution, so you plug a into here and you plug a into there, and let's say you get 0 on the top and you get 0 on the bottom, then you can apply L'Hôpitals. Or if you get infinity on the top and infinity on the bottom, then you can apply L'Hôpitals. So all you do to apply L'Hôpitals is you take the top derivative and rewrite it on the top, and then you go to the bottom, take the derivative, and rewrite it on the bottom. So am I using the quotient rule here? No. Okay, do not use quotient rule. You just take the top derivative, put it on the top, take the bottom derivative, put it on the bottom, and then you can just do a direct substitution again. Okay, and a lot of times, I mean, every once in a while, especially in this lesson, you'll see where you have to do L'Hôpitals more than once. But a lot of times, all you have to do is take the derivative and then re-plug in, and you're good to go. But it has to be in these forms. If it's not in one of those forms, then L'Hôpitals does not apply, and you can't use it. Okay, so any questions? Okay, so let's go ahead and do some examples here. All the hint says is if we have 0 over 0 or plus or minus infinity over plus or minus infinity, then we can apply L'Hôpitals. So let's try direct substitution. What do I get if I plug 0 in to the top and bottom? 0 over 0. So go ahead and write 0 over 0, therefore L'Hôpitals applies. I was told that you have to write that in order to use L'Hôpitals. That it's a 0 over 0 or an infinity over infinity, therefore L'Hôpitals applies before you actually apply L'Hôpitals. Now what our book uses is an equal sign with an H above it, and that's saying I'm going to apply L'Hôpitals to it. So you leave the limit part just the way it is. And then what do I do to the top? 2x, take the derivative. And the bottom turns into 1. Do a direct substitution again, so plug 0 in now. What do I get? 0, right, because I get 0 over 1. Questions on that at all? No, it is really easy. Okay. Okay, let's move to the next one here. It's just one of those things, like if you don't, it never even used to be on the AB test, it'd always be on the AC test, but I always taught it to AB students because it makes a lot of limits quicker and easier than, you know, how you have to try to solve limits sometimes by multiplying by conjugates and weird stuff like that. Sometimes L'Hôpitals will just simplify it really quickly and easily, so. Now there is. They switched it, so now AB has L'Hôpitals on it. So sometimes it's the only way to actually solve a limit. Okay, so if I plug in 0, what's e to the 0? 1. So 1 minus 1 is going to give me 0 on top. Plug in 0 on the bottom, I get 0, obviously. Therefore, L'Hôpitals applies. Okay, then we're going to apply our L'Hôpitals. Okay, what's the derivative of e to the 2x? 2e to the 2x, right? It's just e to the 2x, and then you times it by 2. And the minus 1 goes away because it's a derivative. The bottom turns into 1 now. So what's my answer there going to be? 2. Everyone see that? Okay, so let's look at the bottom one here. Okay, we're going to plug in pi over 2. Sine of pi over 2 is what? 1. So on the top I've got 0. And on the bottom I've got 0. Now in the homework, L'Hopital's doesn't always apply. So if L'Hopital's doesn't apply, then you have to try to solve the limit a different way, okay? Okay, so now we're going to actually apply L'Hopital's. I got room down here, so I'll just move down. Okay, what's the derivative of sine of x minus 1? Cosine of x. And the denominator is going to turn into 1. So what happens when I plug pi over 2 into cosine? 0. Questions at all on the easier ones here? Okay. Okay, so we're going to go ahead and look at these ones that are a little bit harder, but that doesn't mean they're crazy hard. So now we're going to go ahead and plug in negative infinity. So that's going to change the top into being e to the what? E to the positive infinity, right? Isn't e just a number, like 2.7 something? So if we have 2.7 something to the x power, that's an exponential growth function. So what's that graph going to do? What's the y value going to do? Yeah, so it's just going to go to infinity, right? And the denominator, negative infinity, when I square it, it turns into infinity. So therefore, we got our L'Hopital's. So what's the top going to change into? Yep, negative e to the negative x, because it's e to the negative x times negative 1. And the denominator turns into 2x. Okay, so now go ahead and do that direct substitution here. So if I put negative infinity in, what do I have in the numerator? Negative infinity on top. Check the denominator, it's negative infinity, so therefore we can apply L'Hopital's again. Because this one wasn't linear in the denominator, so it didn't just turn into a number down there. So now we just apply it to what we had over here. So I'm just going to show that I'm applying L'Hopital's. And the numerator turns into what? Back to e to the negative x. Everyone okay with that? And denominator is what? 2. So what do I get when I do my direct substitution here? So the top is infinity, denominator is 2. What's infinity divided by 2? Infinity. Okay, so I end up here with infinity. And then that is okay for an answer on the AP test to write infinity. What would be a better answer? It does not exist, okay? Because isn't it possible that maybe you messed up a positive or negative along the way? And you get infinity for your answer, but it's supposed to be negative infinity. So you end up losing your answer point if you have infinity and it's supposed to be negative infinity, but do you get your answer point if it says does not exist either way? Yeah. So what I would do is I would go back and I'd erase that and I would just write does not exist here. Yeah, but usually the limit ones that are on the free response, usually they're just worth a point and it's your answer. And a lot of times the answer is not like does not exist or 0, but those are the most common answers. I mean, a lot of times you're like e squared over 4, and you're like, yeah, I wouldn't have just guessed that. But if you're just trying to guess, I would just guess does not exist because it's something, you know. But sometimes they'll show or get you points for your work and then points for your answer. But this way, at least you get the points for the answer, even if you messed up a negative in your work, okay? What's wrong with 5? Not necessarily wrong with it, but why can't we really do anything with it right now? Yeah, there's no numerator, denominator going on. And I think this says e to the negative x, right? Now, if we just try to plug infinity into here, we would get e to the negative infinity, which goes to what? 0. If you think about the graph I drew that looks like this, as my x's go to negative infinity, aren't my y's going to 0 here? So this part's 0, and this part is what? Infinity. You cannot take 0 times infinity, because 0 times anything is 0. Infinity times anything is, you know, infinity or negative infinity. These are like polar opposites, and we're not sure which one's stronger, okay? Because this is approaching 0, this one's approaching infinity. It could hit anything in between. So you want to try to apply L'Hopital's because we're doing a L'Hopital's lesson. So we want to write this as a quotient. So before we even start, we're just going to rewrite it. Ideas? Which one do you think I might want to move to the denominator? I want to move this one because it's a negative exponent. And what's going to happen when I move it down? It just turns into e to the x. And now if we plug into that, is it a L'Hopital problem? I get infinity over infinity, right? So the numerator turns into half x to the negative a half, and the denominator e to the x. I would probably try to rewrite that fraction without the negative exponents and without the fraction. So this is not a L'Hopital piece here. This is, whoops, not a L'Hopital piece. This is just what it's equal to. So what lands in the numerator if I try to clean that up? Just 1. And do you see how the 2 here is going to land in the denominator? It's a half. E to the x is already in the denominator. And this is going to turn into what? Square root of x down here. So what happens when I do my direct substitution now? 1 over, there's infinity and another infinity, which is going to be multiplied to be infinity. So if we get 1 over infinity, what do I get? 0. So our answer here would be 0. Okay, now 6, we got 2 pieces here. And some people like to think that you can just, you know, do each piece separately, but with L'Hopital's, it's got to just be 1 fraction. How can we get that to be 1 fraction? Get the common denominators. Okay, so we're going to take natural log of x times x minus 1. So this first one we need to multiply by x minus 1 on top and bottom. And the back one we need to multiply by natural log of x. Does that say as we're approaching 1 from the right? Okay. So the numerator here is going to be x minus 1, and then we're subtracting, don't forget about the negative there, natural log x. And the denominator is natural log of x times x minus 1. And do not try to cross out those x minus 1s or natural log x's or anything like that. Okay, you have to be able to factor the entire thing out of the numerator and out of the denominator for them to cancel. So if we try to plug in now, in the numerator we get 1 minus 1 minus, what's natural log 1? 0. So we get 0 on the top. And the denominator I get what? 0. Any questions so far on this one? so what is the derivative on the top there? One minus 1 over x sounds good to me. And the denominator? That's part of it. Okay, so what do I have to use in the denominator? Product rule. Okay, this is a product. There's two different things. So let's leave natural log x alone first, and the derivative of x minus 1 is 1, and then plus. And we leave the x minus 1 alone, and the derivative of natural log x is 1 over x. Okay, I'm going to give you a minute to work on algebra there, okay? And then we'll come back to finish that. So I'm assuming you guys multiplied the 1 over x through in this chunk here. So let's do that part. So I've just got the limit. As we're approaching 1 from the right, on the top I just got 1 minus 1 over x. And on the bottom I've got natural log of x plus, what's that going to turn into? 1 minus 1 over x. How can I clean that up without the fractions? It'll just make it easier when we do the next L'Hopital's. If you left it like this, how many people left it like this and tried to apply L'Hopital's there? Okay, and you can. It just might not be as clean looking, or it might make it a little more difficult of a problem. There's a couple ways you can clean up this fraction within a fraction. There's the long way and there's the short way. So the long way is what you probably learned back in Alg 2, because everybody can do it and it doesn't confuse large amounts of people, but people are really good at math. They like this way better. But the long way is to get a common denominator up here, get a common denominator here. So we have a fraction on top, fraction on bottom, and then what do you do with the fraction on bottom? Yeah, you reciprocate it, right, and multiply it. So you can do that, that's fine. The quick way to do it is to take the top times your least common denominator and the bottom times the least common denominator, because you have to multiply them by the same thing. But do you see how just multiplying by x is going to get rid of those denominators we don't want there? So the top is going to turn into x minus 1. Do you see how that's easier to work with for the next step? If you don't do it that way, you can still get there. The bottom, we've got x natural log x plus x minus 1. And the only bad thing I would say about this is now we have a product here that we have to probably deal with. But let's try a substitution. What do we have on top? 0. So check the bottom. We get 0 plus 1 minus 1, so we do get 0, right? So we're just going to have to apply L'Hopital's again. So the top turns into 1, right? And the bottom here, you just have to make sure you use product rule on this first chunk. So I'll leave the x alone. Derivative of natural log x is 1 over x. Plus, leave natural log x alone. And the derivative of x is 1. And then plus 1. What's that going to turn into in the denominator? Natural log of x plus 2, right? Because we got 1 here, 1 here. And then try a substitution. What do we get for an answer? It's one of those fractions. We get scared. So the top's just going to be 1. Denominator's going to be Yeah, so just do natural log of 1 is 0, and then plus 2, so 2. And that's your answer there. Questions? Okay. You guys have time to work on homework then here? Okay, we're going to look at the 3-3 homework, number 20 here first. So 20 is on page 221, and it says, sketch a graph of a function that satisfies all the conditions. There's a vertical asymptote, so I always sketch this stuff in right away. Vertical asymptote at x equals 0, which is also known as the y-axis. And then it says that the first derivative is greater than 0. What does that mean if the first derivative is greater than 0? It's increasing. Okay, so the graph is increasing if x is less than -2. So at -2 on this side of it, the graph is increasing. And then it says that f prime of x is less than 0 if x is greater than -2. So that means what's happening to the graph? It's decreasing. So over here it'd be decreasing. And it says not at x equals 0 because there's that asymptote there, but it should decrease, and that should decrease over here as well. And then we've got the second derivative. What does the second derivative tell me? Second derivative tells you the what? Concavity, right? So it should be concave up or down if it's less than 0? Down. If x is less than 0. So over on this stuff here, it's concave down. So just so when I sketch it, it'll be easier. And then the other part says the second derivative is greater than 0 if our x is greater than 0. So that means it's concave up. So it should be concave down here. What's going to happen at -2? There's going to be a what? A max, because it increases, then decreases. So it doesn't matter where your max is. It could be way down here. It could be way up here. That doesn't matter. And we have to make sure it looks concave down the entire way, and it increases on this side. So it should have that concave down type shape on this side, and the concave down type shape on this side. And there's an asymptote there, which means the graph should approach that. So does that satisfy the increasing, decreasing, and concavity on that side of the graph? Okay, then we're checking over here. It should always be decreasing and concave up, which sometimes confuses people. Decreasing means it's going down, and concave up means it's curved up. So it'd be something like this. It should approach that asymptote. So that would work. Questions on that, or does that look okay? Really putting this stuff across the bottom makes it a lot easier to work through it. Okay, then we'll look at 52. That one's kind of quick. So 52 will be on the next page. It's talking about coffee is being poured into a mug. And we've got the shape of the mug is kind of like this, where it's skinnier in the middle and wider on the top and on the bottom. Okay, so it says coffee is being poured into the mug shown in the figure at a constant rate. So it's being poured at a constant rate. It's like when you turn on the faucet, okay, and the water's coming out at a constant rate. What's going to happen when you're filling this mug up? Is it going to look like it's filling up really fast or not so fast when you're starting, when it's really wide? It looks like it's barely filling up, right, when you're filling up a big container. What happens if that container gets skinny? What does it look like? It looks like it's going really fast, right, because it's going up really quick at that spot. And then it's going to slow down again when it gets wider. So let's answer the question. Sketch a rough graph of the depth of the coffee in the mug as a function of time. So as a function of time means this is going to be our time down here. And this over here is the depth. So what should be happening to the depth of the coffee always when you're filling it up? It should always be increasing, right? So the graph should always be increasing. Is it increasing a lot or not a lot to start with? Not a lot. And then what's going to happen when it gets to that skinny part? It's a lot. And then not a lot again. So it'll be kind of like this sidewards. Starts at 0, not a lot, gets to be a lot, and then not a lot again. So it should be concave up over here and concave down over here. Account for the shape of the graph in terms of the concavity. So we've got our concave up here. What's this point going to be called? Inflection point. Good. And then this is concave down. What is the significance of the inflection point? Where would the inflection point occur on this mug? At where it's the skinniest, right? So the inflection point occurs where the mug is the most narrow. Okay, 53 is definitely a difficult question, especially when you haven't seen anything like it before, but you should be able to at least start thinking about what all these things mean and what you might be able to do with it to get somewhere with this problem. So with 53, we're given this function. It says it's a cubic function. There's a local max value of 3, which means the y value, at x equals -2. So this is our local max point. And there's a local min value of 0 at x equals 1. So we've got our two max and min points here. Aren't the max and min points going to actually land on the graph? Okay, so if they land on the graph, you should be able to plug them in. So let's plug this one in to the function. We're going to plug this in for x and plug this in for y, or f of x. So it's going to turn into a 3 equals. What's this going to turn into? What's -2 cubed? So -8. So -8a. Okay, then we have our bx squared. Our x squared is going to be +4. And then we got our b with that. The c is going to turn into a -2c. And then plus d, right? There's nothing getting plugged in there. Doesn't seem like we're getting anywhere yet, but we'll get there. Now we're going to do the same thing with this one. So we've got 0. Plug in for x, so we just get what? A plus so all of them will just be 1 with them, right? Okay, so think back to like Algebra 1, or maybe 8th grade math, or 7th grade math, or I don't know when you learn it. It's so long ago. Okay, so when you're trying to solve something that looks kind of like this, let's pretend the c's and d's aren't there. You have two equations, you have two variables. You can do substitution or elimination to solve those, right? If we have 4 variables, how many equations do I need in order to solve it? So 2 equations. When you have 2 variables, 4 variables, you need 4 equations. Okay, we only have 2 of them here, so then we have to think more about, calculus here for a second. With calculus, what's going to happen at the max? What happens at the maximum? The derivative's going to be 0 even, right? It changes from like your positive to negative. Okay, so it's going to be 0 at that spot. So we're going to take the derivative. What's the derivative of this? 3ax squared plus 2bx plus c. Okay, so the derivative is going to equal 0. So this is going to be 0 over here. And what's the x value when the derivative is 0? Let's say we're talking about the max there. Isn't the x value negative 2 when the derivative is 0? So we can plug negative 2 in for the x, which gives me what here? $12. Okay, plug negative 2 in for x here, and we get minus 4b, look okay? And then plus c. Okay, same idea with the local min. So I'm going to let you guys try that one. Try to get that last equation. And then I'll show you a really quick way to solve that tomorrow without having to do substitution and elimination. Sound good?